this recording. Good morning. So I'd like to conclude the exposure to the new concepts, if you will. So remember in our packet, not that you have to turn to it right now. So we have, an outline of the topics, and these are the three that remain. So, we did kind of an overview of this the other day. Before we dig into the plan for today, I just want to make sure if you're looking at this, eudiometers, they can also be called gas collecting tubes. That is just a particular device that you can choose to collect a gas in over water. We addressed that the other day. So you may look at this and say, like, wait, eudiometers, we didn't quite talk about that. So it's not necessarily like this. It shouldn't be a bolded topic, if you will. Okay. So what I would love to do is to warm up with some gas stoichiometry, 2 problems, and then go ahead and tackle these concepts with sample problems. Then do a practice free response that'll help remind us of the theory. Then we'll see what time we have left. At the back of your packet, there are some really, really good multiple choice samples that will really stretch us, but also show like what is the level of understanding that we need to have. So the way that I'm foreseeing class today, we will warm up with some gas stoich. That will give a good measure of, okay, what kind of stuff do we have to do with this? Finish by problem solving. So that'll probably be our first period together. 1 free response that you'll be able to do partner or individual if you want. And we'll see with the rest of our time, we'll probably be able to dig into some of these multiple choice. All right, concerns before? Yes. Yeah, that's okay. I know it's hard to keep track, especially when there's a disruption to the schedule like yesterday. Oh, heck. I'm confusing the date, the day of the week, the letter. Yeah. So, yeah, you're not alone. So, I'm sure we've observed. Why is Robert the sole gentleman on that side of the classroom? Do you see how we're like cut, guys? Like seriously, like look. Interesting. All right. So the page, sorry, I stuck this in there and it didn't get numbered. So it is the page opposite of page 18. So I'm not going to call it 19 because the back of it is numbered 19. Okay, so here are our 2 questions that I'd love for us to start with. So this first just has 2 things that we're answering, and the second has 1 thing that we're answering. Okay, dig in individual with each other. How about if I put the answers here? So as you're finding them, you can check yourself, and I'm going to walk around to address any concerns that you have. So let's just see where we are in about 5 minutes. Okay, go. You do not have to do all your converting, you know, like I do. You could do that separate. Okay, so you will be given R. And so lean on it to inform you as to what you're going to see. Oh, sorry. Colby, any direction needed? Dylan, okay? And we're clear, right? That the mass, we have to make sure that we realize that's not the mass of the NaCl, that's ClO3. That's the mass of the impure sample that we're trying to find how much of it is pure. Yeah. So it's so easy to get misled. Good. Lindsay, good? Okay. Yes.
So you can stay in Tor, like if it doesn't tell you to stay in Tor, you have to switch to ATM.
If we're employing R. If we're employing R. However, if you're just doing P1 V1 equals P2 V2, unless it says find the pressure in, as long as it's a unit of pressure, you can keep it. Yeah, definitely. Yes, sir.
For the mass percent, do we just, so that's not like final answer?
No. Yeah, so the final answer. So we found first, okay, how many moles of oxygen did we collect? And then, well, how many of grams of the reactant must have been reacted? So that's the pure over the impure times, yeah. That's what we have to be able to do with gas stoichiometry. Okay, clarification needed at all. V equals nRT. In honors chemistry, I always nickname it the fairy godmother equation, because a fairy godmother, whenever she's called on, she just flies right in and just waves her magic wand and makes whatever's needed, or, you know, the dress, the carriage, or whatever else. Well, as far as the ideal gas law, what is the magic wand? The constant. The constant is what allows us to not be at STP or at ST. It doesn't matter. So we can apply P equals nRT whenever we need, no restrictions, like on molar volume. So that is definitely, as soon as we realize we're dealing with gases, P equals nRT should come to mind. All right. Questions for me? So let's get to a little bit of new territory. So in our packets, if we could find, please, oh, the very next page. Okay, so we know per the kinetic molecular theory of gases that kinetic energy is directly related to temperature. We know that. And I told you that we won't be calculating a value. We just know that those go hand in hand. So the greater the temperature, the greater the kinetic energy. And if you have two gases at the same temperature, they'll have the same kinetic energy, but not the same velocity. Not the same velocity. Now, we said temperature is a measure of the average kinetic energy. And we know that number of particles, and then we say kinetic energy, that, okay, temperature is going to give us the average, but there's a span. So do we just calculate the speed of the average? Well, something better has been given to us. It's called root mean square velocity. And I have here, just because I wanted to give us some kind of foundation of what is a root mean square. I love that Zumdahl, your author, just says, it's just a special kind of average. How do we take a proper average of so many variations? That's what this does for us. That's all we need to know. All we need to know. Okay, this is how Zumdahl presents the equation. But I tell you what, when I see a capital M, I think molarity. So if it's okay with you, I always will show what this is to be as MM, capital MM. So what do and what is this really? Not molarity, molar mass. Yeah. Okay, so this, look at that's kind of fun. It's like a mu with an RMS, that's root mean square. So this will be our velocity. And usually what are the units on velocity? Meter per second. You got it, meter per second. All right, and we know, Connor, that capital T is, and dealing with gases, what unit should that be in? I am so glad. So you were just seeing who was listening. So we know we measure Celsius, but we need to be in Kelvin again, just to circumvent, having so often 0 degrees Celsius. So, okay. Temperature is the average kinetic energy. But what did I say? Even gases that have the same kinetic energy will have different speeds because it's dependent upon the molar mass. So looking at our equation, Justin, the lower the molar mass, now common sense would just lead us here. Does the equation support it? The lower the denominator is, what should happen to our end result? Yeah. So we can cite this equation if we are asked to compare speeds or something else. We can always say, well, this gas will have a greater speed per the root mean square velocity, or that just the smaller the molar mass, the greater the speed. But if we can back it up with an equation, that's always good. Okay, R. So this is where we need the other version of R, the other version of R. So 0.08206 liter M is for Kelvin mole. That's PV equals nRT. Where on earth do we get meter per second out of Kelvin, and then molar mass is going to be gram per mole? Huh? Okay. Well, I didn't mean to do that. R. I will give you these. You don't have to know. Okay. But the R we need here is the 8.314, and it will always be given as joule per mole Kelvin. Oh, I'm so sorry. Joule per mole Kelvin. Okay, so there again, how do we get meter per second out of that? A joule is equal to 1 kilogram times meter squared per second squared. That doesn't seem, because I'm trying to think, is it meter per second squared, but we need. Because if, right? Oh, that's a Newton. I know that's what it is. It has to be that.
What was the unit for again? What half mv squared and v squared is m squared over s squared.
Okay. Say that one more time, Alan.
A joule is the unit for again.
Yep.
Is mass times velocity squared. So it should be m.
There we go. Right? So then we're okay.
Well, it'd be the same thing. It's squared.
Exactly. But I was just questioning myself. We'll see. Yeah, I don't. I'm pausing. The deal is, this is how we get meter per second. So let me just show us. So what we'll end up doing is taking the square root of 3 times 8.314, and it'll be kilogram per meter squared, or kilogram meter squared per second squared, times the temperature in Kelvin. Okay. No, oh, never mind. Silly Gerhardt. This is where okay, a joule is this. That gets substituted in for just the joule. So it's kilogram per mole Kelvin, meter squared per second squared, right? So this, if this is what a joule is, a kilogram meter squared per second squared, right? So I'm just implementing that here, but it's still divided by mole Kelvin. That's how we get this crazy stuff. Okay, and then that's divided by, what does our molar mass unit have to be? Gram per mole? Kilogram per mole. So that's a little bit of a glitch here. Okay. So then if we see, okay, Kelvin's canceled, good to go. This is the numerator and the denominator. So those will directly cancel, right? The denominator of the numerator becomes the numerator of the denominator. Is that okay? So then we'll be taking the square root of meter squared over second squared. So ta-da, that's how we get meter per second. So sorry that I had a memory block there for a second. Okay, the deal is, we will be asked to solve for one of two things. We'll be asked to solve for one of two things, either the root mean square velocity. So then you have to be careful, make sure we use the 8.314 and make sure our molar mass is in kilogram per mole. Or we're solving for molar mass. So we have to be careful to use 8.314. Just make sure that we're doing our algebra steps correctly, but realize we're going to get kilogram per mole. Just so I don't forget to address this, what is a reasonable molar mass for gases under room conditions? Are they going to be like 300, 400 grams per mole? Probably we would expect under, I would say usually under 100 gram per mole. But it would be okay if we're like 126 gram per mole. And of course, if we would, have a really high temperature or something. So just to have us check the reasonableness of our answers, but we may like shake in our boots if we get an answer that's 0.100. We have to realize that's kilogram per mole. That's 100 gram per mole. That's reasonable, right? Okay, so really a pretty straightforward equation. Are we okay, Alan, keeping neon, or would you like another gas? All right, so at 25 Celsius, which would be room temperature, what is the speed of neon? We have a small amount of it surrounding us. All right.
Just multiply the R value by 1,000 grams per.
Oh, absolutely. Absolutely. Yeah, you definitely could. Yes, that may be a more comfortable option. Thank you. Our wingspan is about a meter. No, not mine. I'm so wimpy, but about a meter. So at room temperature, neon is traveling at 607 meters per second. Something. So, not bad. We could be asked to find our speed, or given speed, find molar mass. So there is a problem just on the next page. Can we go ahead and give this a whirl, and then we'll break for homework? Yes. I know, yeehaw. Thanks. problem asked to find molar mass, it did not say in these units. So if we did not do what Brendan suggested, which is absolutely fine to do, absolutely fine to do. If you went ahead and got this to be gram meter squared per second squared Kelvin mole, then you're going to get gram per mole out. But if you don't, you're getting kilogram per mole, but you could leave it like that because it didn't specify exactly the unit. Questions? Okay, we just have two other things to touch on related first to speed, and then we're going to improve upon, if you can imagine, the fairy godmother equation. We're going to make it real. So, all right, we will break for homeroom. If you have any questions over the problem solving that we did, please let me know.